The continuation of the questions related to specific heat and the latent heat. A polystyrene cup holds 250 grams of a water at 20. In order to cool the water, to make a cold drink, a small piece of ice is added until it reaches zero. So like we have a polystyrene cup, which is filled with water. To make this cold water, we add ice cubes. So water will lose energy and the ice will gain energy. The water initially at 20 and then the water reaches zero. How much we have the specific heat capacity of a water is given and specific latent heat of fusion of ice is also given. The question is calculate the thermal energy lost by the water in cooling. Because water is cooling, it means there is a change in temperature. Whenever there is a change in temperature, which formula we use? We always use a formula E is equals to Cm delta T. E is the energy supplied or removed. Specific heat capacity. Remember one thing, if the mass is in gram, like specific heat capacity or specific latent heat in joule per gram or kilogram, mass should be in, like the unit should be same. If this is gram, this should be gram as well. We don't have to change the unit, so it's 4.2 times the mass 250 times the temperature change. So it was initially 20, but then reaches zero. So the temperature change will be the temperature change will be 20 minus 0. We substitute, we'll get 21,000 joules. State the thermal energy gained by the ice. What we assume here, we assume that what energy is lost by the water, all the energy is gained by the ice. So it's always, as I mentioned, whenever you're working out a temperature change, it is always greater minus smaller. The formula for temperature change, because it's a scalar quantity, so the sign does not have too much significance here. And what is our assumption? Our assumption is that all of the energy which is lost by the water is gained by the ice. So water is losing energy, the ice will gain. So if water lose 21,000 joules of energy, we assume all the energy is gained by the ice. So same answer you will write here, 21,000. And then calculate the mass of ice added. So ice is melting, so energy is mass into latent heat. We have the energy, we have the latent heat is given, so we can work out the mass. 63.64 grams of the ice will melt or added to this. In question 22, the temperature of a person of mass 60 kilogram falls from 37.2 to 36.7. Calculate the thermal energy loss. Because there is a temperature change, whenever in a question you have a temperature change, so energy is equals to Cm delta T. So specific heat capacity of the body is 4,000. The mass of a body is 60 and the temperature change is 37.2 minus 36.7. We multiply all of them, we'll work out, it will be 1.2 exponent 5. That is the amount of energy which is, or 120,000 joules of energy that is lost from the body. And this can use to, the cooling of a body was entirely due to evaporation of a sweat. The mass of the sweat which evaporates, the specific latent heat of a sweat is given. So what we assume like if this is representing a body, what energy is lost by the body, same energy is absorbed by the sweat. So here answer, which was 1.2 exponent 5 joules, this whole energy is absorbed by the sweat. So we'll use the formula E is equals to mass into latent heat. Energy, we have this value, latent heat is given. So we can work out how much mass of the sweat will like evaporate, which is 0.05 kilogram. Question 23. A pan which contains a water boiling at 100 standing on heated hot plate for 20 minutes, 0.075 gram of a water is turned into steam. The latent heat of vaporization is given because there's a change in state. So energy is mass into latent heat. The mass is 0.075 and the latent heat is 2.25 into 10 to the power 6. When we multiply 168,750, 168,750, and the energy will be joule. So because they hear this change in state, that's why energy is mass into latent heat. Then a hot plate is operated for 20 minutes. We need energy. Energy, that's good. Energy is VIT. When energy is power into time or energy is VIT, it depends on if we have voltage, current, and time. We'll use this one. So voltage is 240. Current is 0.65 and the time is 20 minutes. We should convert into second. So we multiply by 60. So 187,200 joules. So why here our answer is different from like what we supplied and what is absorbed is different. So 168,750. This was what we work out, it was absorbed. And this is what we supplied. Why they're not same? Because not all the energy absorbed by water. That's right. Like some of the energy lost to surrounding. So what we supply or what is supplied from the heater, some energy is lost to the surrounding. Then what is meant by the specific heat capacity? The energy needed to change the temperature of 1 kilogram substance by 1 degree centigrade. You have to learn the definition. A student carry out the experiment to find the specific heat capacity of a block of aluminium. He's having a mass. Yeah, that's right. He's having a mass, he's having a power, time, temperature, initial and final. So whenever the temperature change, remember whenever the temperature change, energy is Cm delta T. But because you are using a heater, so for electrical heater, this energy is power into time. So we can say P into T is equals to Cm delta T. So we have the power. We have power is 420. We have the time 95 seconds. Specific heat we don't know. The mass of the block of aluminum was 2 kg. The temperature change is 40.5 minus 19.5. So this whole is multiplied, other side will be divided. So the specific heat capacity, when you substitute, it will be 950 joule per kilogram degree centigrade. So remember, temperature change equals Cm delta T. State change E is equals to M into L. But for IGCSE students, only two formulas you have to learn. One is energy is power into time. Another one is E is equals to Cm delta T. For GCSE, all three formulas they have to learn. In experiment, no attempt is made to prevent the heat loss. So there's two actions which will minimize the heat loss. Lagging, okay, one thing, good. What else? How we can? Initial and a final temperature, both should be less than the room temperature. Both. So that it won't lose energy. Using draught is also. Here we don't want to maintain your paint the block, also minimize the heat loss, but the reason why we cannot say water bath, because water bath is usually used to maintain a temperature. We don't want it to maintain a temperature. We want it to increase the temperature. So water bath is not acceptable. Water bath is only in the case when you want to maintain a temperature. Figure shows water being heated electrically. The water is in a can. It's not boiling but evaporating. Describe in terms of movement and energies how evaporation take place. So how evaporation take place? The most energetic molecules at the surface gain energy and break the intermolecular force and escape. And don't forget to mention the break the intermolecular force, like breaking the attractive force between each other. How evaporation and boiling are different, as we already discussed this, evaporation occur at any temperature, boiling at a specific, evaporation only at the surface, boiling throughout, evaporation, no bubbles, boiling bubbles. Then we need this latent heat. So energy is mass into latent heat. We have the power, so energy will be power into time, mass into latent heat. We have power, we have time, we have the mass as well, so we'll get the latent heat. So 60 into 120 will give us the power and divide by 3.2. So we'll get joule per gram, the value for latent heat. That's how much? 7,200 divided by 3.2. 2,250. Okay. Then in question 26, equal volume of a nitrogen, water, and copper at 20 are heated. Which one will expand greater expansion? So this is a gas, this one is a liquid and solid. So the gases expand more than liquid and liquid expand more than solid, because in a gases, the particles have a weak attractive force. So reason is it's of 3 marks, how you score, like 1 mark is for mentioning here nitrogen. And how you score the remaining 2 marks, you will compare the force of attraction. The forces. We'll mention like in nitrogen, the gases have weak force of attraction. The particles are moving at a high speed, where in liquid, the particles are actually closer to each other, moving around each other, and solid, they're tightly packed. So that's 2 marks. One is for this 3 marks, one is for nitrogen, and remaining 2 marks are for explaining each of them. There are strong bonds, you can say, as well in a solid. A mercury in a glass thermometer is placed in an insulated beaker at 60, and the water is heated at a constant rate. The temperature for water is measured and recorded on the graph. State the effect of heat supplied during 5 minutes. First 5 minutes, what is happening? When we supply, the temperature is increasing. So when the temperature is increasing, how we explain in terms of particle, we can say that the particles are moving faster or kinetic energy increases. But then from 5 to 20 or onward, what happened? The temperature does not change, so there's no change in kinetic energy. Yeah, the water boils. That's also correct. Not water. Place in a, yeah, water. Yeah, I thought it was a mercury. But mercury thermometer is there and water is a liquid. So you can mention a water boils from 10 to 15. This is a similar question about it's measuring the specific, like what readings we should take and how we work out and why there might be difference. It's the same question we discussed earlier. In question 29, some water is heated electrically in a glass beaker. Experiment to find specific heat capacity of a water. The temperature is there. Use a graph to find the temperature rise in first 120 seconds. So it is 20 here, 20. and then it is 40. So how much temperature rise? The temperature rise by 20. Because it was 20 in the beginning, and then after 120 seconds, it is 40. So how much it rises? It is by 20. But the next 120 seconds, so it is at 120, it is 40. And whenever you're solving a question from the graph, you should draw these lines to show clearly on the graph that how you worked out the answer. So this one is 55, 40. So the next temperature change is from 40 to 55. But the initial temperature change in the first 120 second was 20 to 40. Why initially the temperature change was 20 and then it is about 15? What's the reason? Why there's a difference in the temperature change? Initially, there was a greater change in temperature, but as the temperature is increasing, the change in the temperature decreases. What might be a reason for that? So yeah, high temperature, so heat loss, greater heat loss to surrounding. Like when there's a high temperature or a greater difference between the temperature of an object and the surrounding, so it emit out more energy to the surrounding. For rate of heat loss. So why these values are different? No, not less energy supplied. We supply, they mention here, we supplied a constant, using a constant power. As you can see here, some water is heated electrically. So electrical heater, its power is constant. The power of the heater is not changing. But why initially the temperature change was more in first 120 and then it's a small? Because initially the water is at 20, it was not losing energy to the surrounding. But when the water become at 40, it lose more energy to the surrounding. So what we supply? Energy lost to the surrounding. Next, we need a specific heat capacity when a temperature changes from 20 to 16, 210 seconds. So energy is Cm delta T. When the temperature change is there, so energy is power into time, Cm delta T. Power is there, which is 60, 210. Specific heat we don't know. Mass is 75 and temperature change is 60 minus 20. And when we substitute 4.2 and the unit, if you're using a mass, because the mass is given in gram, so you will use, like if you substitute the value in gram, then it will be 4.2 joule per gram degree centigrade. If it was if you use your mass in kilogram, then it will be 4 joule per kilogram degree centigrade or a Kelvin. Figure 30 is about the specific latent heat. Ice is melting. In order to obtain an accurate result, state why it is necessary to wait until until water is dripping into a beaker at a constant rate. Because when the water starts to drip at a constant rate, it means that all of the ice had reached 0 degree centigrade. Use finely crushed ice rather than large pieces. Finely crushed ice have large surface area, so it will melt at a faster rate, so easily melt. Yeah, large pieces will take more time. There's small surface area. The power of the heater and the time are known. Write down other readings which we need to get the latent heat of fusion. So energy is mass into latent heat. So power into time is mass into latent heat. We have the power and time. So what else we need? We need the mass of the ice here. We have to measure the mass of the ice before, like when the constant dripping start and when we finish the experiment. Because when we start supplying the heat energy, why we should wait until the water is dripping constantly? Because say you switch on the heater. When you switch on the heater, maybe the ice nearby the heater might be 0. But ice which is far from this heater may not receive that heat energy, maybe at -4. But the ice start to melt because the surrounding ice is melting. So what we will do, once all the ice reaches 0, the constant dripping start. When the constant dripping start, we'll measure the mass. So we will measure the mass when the constant dripping started. And we'll measure the mass again once we finish the experiment. Because when the constant dripping start, maybe the mass, some of the ice might be melted, say the mass was 30 gram. When we finish the experiment, maybe the mass might be 35. So how much mass is melted? So how much mass is melted? It will be 35 minus 30, which will be equal to 5 grams. Is it clear, this one? So why the last, that part was of 2 marks? Because we should measure the mass when the constant dripping start and then measure the mass again. Then working out the latent heat, we have a 40-watt heater, we have the power. 16.3 gram of ice is melted in 2 minutes. And the heater is then switched off, and in 2 minutes, 2.1 gram is ice melted. Why this ice is melted? Look, first when the heater was switched on, how much ice was melted? 16.3 gram. When the heater is switched off, in 2 minutes, how much ice is melted? 2.1 gram. So how much ice is melting because of the heater? This is the amount of the ice which is melting because of the energy we supplied directly from the heater plus surrounding. So ice is absorbing energy from the surrounding. Yeah, its heater is still hot, so it is also supplying energy. So what we do, we subtract the two masses to know how much actually the heater is causing or melting the ice. So how much ice is actually melted? We have 16.3 when the heater was switched on, and we have 2.1 when the heater is switched off. So when we take a difference, we'll identify a rough idea that how much or actual ice is melted when the heater was on. So 16.3 minus 2.1, which is 14.2 grams. And we have the time in minutes is there, or 120 seconds. So to get the latent heat, energy is power, and energy is mass into latent heat, energy is power into time, mass into latent heat. So we have the power of the heater, we have the time 120, we have the mass, we can get the latent heat. Why we subtract the two values from here? To just have a rough idea that first the heater was causing melting the ice as well as surrounding, and then the heater, like how much ice is melted because of the surrounding, or the heater is also still hot, so how much heat energy because of that part. So we subtract the two masses. Question 31, you have to learn the definition: specific heat capacity, amount of energy required to change temperature of a given mass by 1 degree. Water is having a very high specific heat capacity. Suggests why it might be disadvantage when using a water for cooking. Like what would be a disadvantage? If a substance is having a very high specific heat capacity, so we need too much energy to change its temperature. Like it take more time by 1 degree, because it will absorb a lot of energy until it changes the temperature. And they can ask this question, why this might be an advantage when we are using a water in a car radiator. So why this will be an advantage? Because the water will absorb too much energy before it changes the temperature. Why? So because in the car radiator or the car engine, radiator is there, the heater is like the car engine is producing heat energy, and the radiator there's a water. So this water absorbs a lot of heat energy from the engine, and without changing or changing a temperature or a very small change in temperature. Coolants, different types of other liquids are also used, but most of them are water based. Like water based means like other substances are dissolved in water. So when having a high specific heat capacity, say this is a car radiator in which the water flow, and this is representing a car engine. When the car engine produce heat energy, that heat energy lost to the surrounding. This energy is absorbed by the water which is present in the radiator. Say this temperature water was at 90 degrees centigrade. Example, when it flow through this around the car engine in the radiator, the water temperature when it will come out from the radiator, it might be 19.2 or 19.1. So why there is a small change in temperature? Because the water is having a very high specific heat capacity. So specific heat capacity and temperature change are inverse. So if the water is having a high specific heat capacity, when it absorbs a specific amount of energy, the temperature change of a water will be small. So it will absorb greater amount of energy before the water being boiled. And it work as a cycle. Like this water enter, escape, then it cool down in losing energy to surrounding, then enter, then escape. So it work as a cycle. So answer is like, because the water does not show a greater change in temperature when it absorbs energy from the car engine or from the system. That is an advantage. But what is the disadvantage of using water for cooking? Like you have to supply, say, if you are cooking any food, we normally use oil. Two reasons are there. One is to provide a different essential nutrients, as well as to cook the food quickly, the faster, because the specific heat capacity of a water is 4,200 joule per kilogram per degree centigrade. So if I have 1 kilogram of a water, it needs 4,200 joules to change its temperature from 1 degree, like 20 to 21. Then another 4,000 to change from 21 to 22. But if the same food, if we cook in oil, the specific heat capacity of oil is low. So what is the advantage of a lower specific heat capacity? Like example, say 700 joule per kilogram degree centigrade. So when I apply 700 joules, the oil temperature increases from 20 to 21. When I apply another 700, so 21 to 22. So we can easily reach a very high temperature, because cooking a food, if we cook at a high temperature, it will quickly cook, because there are chemical changes. So it will cook quickly at a high temperature as compared to a low temperature. Is it clear, the last part? How it can be advantage or a disadvantage in different situations? Any doubts? Okay, so figure 9.1 illustrate an experiment to measure the specific heat capacity of some metal. A piece of a metal is heated in a boiling water. So what is the temperature of a metal now? Because it's in a boiling water, so the temperature will be 100. When we place this metal, it's 100 and it lose energy to the water. The temperature rise for a water and temperature fall for a metal. So because they mention it's a boiling water, what is the temperature of a boiling water? It is 100. So if the boiling water temperature is 100, now initially when we transfer, first it is in a boiling water, so the temperature is 100. When we transfer, the water temperature and the metal temperature are different. Then because they have a difference in the temperature, so heat loss from metal to the water, heat loss to the surrounding, like to the water. So water is a surrounding. So the temperature of the metal will decrease and the temperature of a water will increase until they reach the same temperature. So this is 100. Mass of a initial temperature of a water in a cup is 21.1. Before we add, final temperature was 22.9. So what will the temperature of the metal when we transfer? It was 100, but then it will be 22 because they will come in thermal equilibrium. Thermal equilibrium means like temperature of the two substances are same, so they don't lose energy to each other. That is what happened. Like if you keep like in a glass, you add water and leave it for some time, that it will come in thermal equilibrium with the room. If a room temperature is 20, the temperature of a water inside the temperature of the water inside the glass will also be 20. So first we have at 100 we transfer. So both have a temperature of 22.9. The question is, state the initial the temperature rise for water. So how much temperature rise for water? Initially 21.1 and then final 22.9. How much it rises? That is 1.8. This is 1.8 degrees. And but for heater, sorry, for metal block, it was 100 and become 22.9. So how much temperature changes for metal? It will be 100 minus 22.9, which is 77.1. So 77.1. Is it clear? The temperature changes? Why not 100 minus 21? Because we want the final temperature change. Like calculate a temperature rise for both of them. So initially we were having a metal which was 100 degrees centigrade. We have a water inside a container which is 21.1 degrees centigrade. We transfer this metal into a container filled with water. So the moment we transfer, this is 100, this is 21.1. Now what happened? The heat energy is transferred from the metal to the water. So when they come in thermal equilibrium, when the temperature does not change anymore, the temperature of the water and the metal the final temperature of a metal and the final temperature of the water, that is 22.9 degrees. So this temperature 22.9, this temperature 22.9. The question is, what is the temperature change of a water? So for water, it started 21.1 and ending at 22.9. So how much temperature change? 22.9 minus 21.1. And what is the temperature change for a metal? We started with 100 and it ended at 22.9. So how much temperature change? 100 minus 22.9. Is it clear, this one? And why the temperature change of a water is not same as the temperature change of a metal? Because they have different specific heat capacities. Like you can see the water temperature changes only by 1.8, where the metal temperature changes by 77.1. So if the temperature change of a water is small, it means it has a higher specific heat capacity. Temperature change of a metal for the same amount of energy is more. So it means the specific heat capacity of this metal is small. So thermal energy gained by the water in the cup. So thermal energy gained is equals to Cm delta T. Specific heat is there for water. M is the mass and delta T is a change in temperature. We just multiply, we get the energy. And assume that thermal energy, what's the answer for this part? How much thermal energy gained by the water? Cm delta T. So 1512 joules. And we assume that this all energy is lost by the metal. So again, we'll use the same formula, E is equals to Cm delta T. So we have the energy 1512, specific heat we don't know, M is the mass of the metal, which is given in the question. Mass of the metal was 0.05 and temperature change is 100 minus 22.9, which is 77. So we divide, we'll get the specific heat capacity, which is 392. And why these values are not same? Because the specific heat of a capacity of, like, suggests one reason, heat loss to the surrounding. You can also say one reason why experiment might not have correct value for a specific heat of a metal, heat loss to surrounding when we are transferring this metal or water absorbed. Mainly it's like when we remove this metal, maybe the metal was not at 100, it was below 100. That might be a reason as well. Question 32.